Hello everyone, welcome back to our reading of categories in Sheaves. This video is going to be very brief. I'm just doing this to plug a gap. In the last video, I wanted to cite a proposition from section 3.1, as you can see here, 3.1.8, but it turns out that actually in my attempt to summarize the section and sort of leave out that stuff which I don't need, I managed to miss one that I would need later on in the chapter. So now we're going to go back and just fill it in. We want these videos to be complete, to reference each other when necessary in the most coherent way possible, so we want to fill in this small gap. So that's what we're going to do. So without further ado, let's get to our proposition. So in our setup here, we have two functors, psi, which will be from, every category here will be small, k to I, and a different functor phi j to I. And we'll assume that psi is cofinal. That's a terrible psi. Much better. So, okay, psi is cofinal. Then under these conditions, we have two statements. First, if j psi k to I psi k, the induced functor, is cofinal for every k, then phi is cofinal. And if k is filtrant, and j sub psi k is also filtrant, then j is filtrant. Oh, yeah, for every k. So, of course, what's going on here is I've got a situation like this. This one is psi, this one's phi. And the point is supposed to be that if I know something about all of the sort of fibers, so to speak, of this guy, then I'm sort of able to transfer this property across this pair of functors. And I don't remember which of the two in the main video that sort of motivated this tangent is what I needed. But so I'm just going to do both, and that way there can't possibly ever be any problems with missing any more facts from this section. Well, never say never. There very well could be. But without further ado, let's just prove it. So first, if I have any functor alpha I to set, then I can calculate as follows. I can take the limit of alpha compose phi, and from the chapter on limits, somewhere in 2.3, I can't remember exactly which result I need, but I can write this as the limit over I in I, and the limit over j in ji of alpha composed with phi of j. This is sort of our evaluation fact. And then this will be the same thing as the limit over k in k, and the limit over j in, I guess I want j sub psi k. Of course, of alpha of phi j. This, of course, though, is the same as the limit when I essentially compose. This will be done now with alpha I. So I get limit k in k, limit I in I psi k, alpha I. Oh, I wrote psi over there. I think this needs to be phi. Sorry about that. Yeah, so this is alpha I, but this is, of course, then same result as previously, limit of alpha composed with psi, limit alpha. Okay, so let's just quickly sort of summarize how this works. At 2 points in here, I use the result from 2.3. I sort of use this evaluation business. And then at two other places, I guess it's the second and fifth isomorphisms, I'm using the cofinality. And the middle guy, of course, uses the induced fact that the J psi to I psi is cofinal as well. Okay, I think that handles this computation. This is my favorite proof strategy ever, by the way. You try to write down a proof, and then you go through and you tack on every hypothesis that's necessary to make your proof correct. And if you sort of stare at this proof naively, all of these isomorphisms that we've got here, well, that's basically what I'm doing. I just sort of wrote down a list of things that are necessary to make this true. Okay, now let's do the second part. It's very similar. So now, again, I consider a functor, this time J to set. And again, from 2.3, I know that the limit of the alpha is evaluated at J can be written as the limit over I, limit over Ji, J in Ji, alpha J. But this guy can be further written as the limit over K, limit over J in J, alpha J. And of course, the reason that this works is that I know that these limits commute because, of course, these forward limits commute with finite projective limits, and this limit functor, just in general, as a functor from functors to sets, commutes with finite projective limits, and so the result follows from 3.1.6 in Kashiwara and Shapiro. Okay, this should conclude our discussion of this proposition. Oh, maybe I should say one more, just a quick thing. This is, of course, the commutativity, the main commutativity result. In 3.1, in case you forgot. But yeah, so I think that's going to conclude this video. Like I said, very brief. I just wanted to plug this gap in what I had covered previously. Okay, until next time, take care.